All right. So I wasn't able to find the video. Maybe I thought I recorded, but I didn't. So I'm going to record for you another video here. All right. So I got the practice problem keyed up. This is week 6 study guide problems number 1 and 2. So here we go. All right. Problem number 1. We have a hybrid carbon Kevlar fabric. I kind of like the picture here so you can sort of see what this fabric looks like. This is a woven fabric. The warp direction is carbon fibers and the weft direction is Kevlar fibers. All right. Carbon fibers run in the 0-degree direction. Kevlar fibers run in the 90-degree direction. After manufacture the composite with a single layer of fabric, the following properties were found with a lamina with a 55% volume fraction. Here we are. Okay, no problem. Estimate the woven composite stiffness properties if 4 layers of this fabric are stacked in a 0, -45, +45, 90 configuration. Okay, so that is a fabric that has been placed 0, -45, +45, 90 configuration. Okay, so this is 4 layers of woven fabric stacked on top of each other. All right, and our job is to estimate what the final laminate properties would be if we stack those 4 layers on top of each other and infuse with epoxy and assumed a 55% volume fraction. Okay, so let's talk about how we're going to do this. Um, this is more or less just going to proceed like a normal laminate analysis. Okay, so the idea is to take E1, E2, Nu12, and G12 for a single layer of this fabric, which those are given to us over here. And now we're going to use those in multiple layers with a particular stacking sequence to calculate a laminate stiffness. Right? We're going to get sort of these A, B, and D matrices. Okay. Once you have the ABD matrices, you can invert to get little a, little b, little c, and little d. And then once you have little a, you can calculate laminate properties, understanding that entries of the A matrix, like the A11 entrance, little a11 is 1 over h times e bar x, negative nu xy bar over e bar x times h, and da 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 da. All right, there's many of these, but really we need nu bar x, we need e bar x, e bar y, and g bar xy. So there's some entries over here, but the 2-2 entry is 1 over e bar y times h, and the 3-3 entry of this is 1 over g bar xy. So once you calculate the little A matrix, then you can get these properties, right? So if you know what A11 is numerically, you know the total laminate thickness H, then you can calculate E bar X, okay? So that's generally the strategy that we're going to go with here, right? Okay. So, I mean, let's talk about that. All right. So step number 1 in all this is we need the Q matrix. All right. So we can calculate Q. This is generally the setup. And in your equation sheet, I guess I'll just get the equation sheet up here really quick. But it shows how to calculate those entries of Q directly. Now, you can calculate them directly, or you could calculate, you know, the compliance matrix S and then invert that. So the Q matrix is also S inverse. So if you like calculating S better and just inverting that, you could also do that as well. So, but let's get the equation sheet out here and I'll show you the calculations that you would need to do to get this. All right. So this is how we would calculate the Q matrix, right? Q11 is E1 over delta, Q22 is E2 over delta, Q12 is nu12 times E2 over delta, where delta is 1 minus nu12 squared over E2 over E1. We have all of these things, all right? All of this we have. So Q66 is G12, so all of those are provided. They're all right here, right? So you can calculate the Q matrix using all of this, right? I will write what it is here then. And you can verify for yourself. 65.1, 2.2, 0, 2.2, 40.1, 0, 0, 0, and then 10, because this is just G12. All right, and this is GPA. All right, so that's step number one, calculating the Q matrix. Done that a bunch, should be able to do that like pretty easily, pretty quickly. All right. Once you have the Q matrix, now we need to start calculating the capital A, B, and D matrices. I'm not going to do this by hand because that would take forever. Okay. But I'll just tell you that like calculating the capital A matrix is summation from little k equals 1 to n of q bar k zk minus zk minus 1. Okay, so we've looked at these and we've done some of these A matrix calculations before. Do this computationally is probably a little bit better. When it comes to the exam, I'm not going to ask you to calculate a full capital A matrix, but you should be able to do like the calculation of one entry of the A matrix, for instance, by hand. Okay. All right. So if you actually go through and work all these out, the B matrix, capital B matrix is 1/2 summation k equals 1 to n of q bar k, zk squared minus zk minus 1 squared. And then the D matrix, remember these are 3 by 3 matrices. This is 1/3 summation k equals 1 to n q bar k zk cubed minus zk minus 1 cubed. All right. And I think week 4 videos would go over how to calculate these by hand again. So if you need some refresher, go watch some of the week 4 study guide lecture videos, okay? But that is generally the formulation and how it gets done. Now if you do that, you'll have the, I mean, you can calculate these yourselves, but you'll end with the following. The capital A matrix is 0.135, 0.030, 0, 0.030, 0.14, 0, 0, 0.053. And this is 1 on GPA for units. Sorry, so GPA millimeter. GPA meter, geez. Right, okay, so that's the calculation of the capital A matrix. Once you have the capital A matrix, you're going to invert to get the little a matrix. Well, let's be a little bit more clear here. The B matrix is also something. The D matrix is also something. I'll put them in here for you. If you want to work through those calculations, you can. This is what they end up being computationally. And these are units of GPA meters squared. This is GPA meters cubed. All right. So this is the B matrix and the D matrix. Once you have the A, B, and D matrices, then the full laminate stiffness matrix is the 6 by 6 that is capital A, capital B, capital B, capital D. All right. And this is a 6x6. This is the full laminate stiffness matrix. Once you have this, you want to invert this. So that would be taking this all to the -1 to get the 6x6 that's little a, b, c, and d. You can't really do this by hand. That would be impossible. It's not impossible, but it would take a long time. It's the inversion of a 6x6. So you basically have to do this computationally. But the point is, after doing this computationally, you have the little A matrix, which is a portion of this bigger 6x6, and this is a 3x3. Right? Once you have the little A matrix, kind of showed this already before, that there are particular entries of the A matrix that relate to the laminate properties, right? So I will just give you the A matrix here, which is the following. So if you did the computations, this is what you would have for the little A matrix. And this is 1 on GPA meters. That is the little A matrix, right? Now, you want to calculate E bar X. We know or note that A11 is 1 on H times E bar X. This is in the notes. It's derived in the notes. Should be able to sort of get yourself there. So that means that E bar X is 1 on H times A11. So here, this is 1 on, the total laminate height is 3 millimeters. This is 0.003 meters times A11, which is 8.045, 1 on GPA meters. So if you work through this, you'll find that E bar X is, drum roll, 41.4 GPA. Okay, so that's E bar X, 41.4. You can do similar things for E bar Y and G bar XY. So E bar Y is 1 over H times A22. You can work through that. That's going to be 41.4 as well. And then finally, G bar XY is 1 on H times A33 or A66, however you want to prescribe that. That here is going to be 17.5 GPA. Okay, so there's a lot to sort of work through there, but it's starting with properties of the lamina. That is one single layer of the fabric as a composite. Then saying, all right, I'm going to build a laminate out of this lamina layer by layer. And doing that, you're just following typical laminate analysis. So there's nothing particularly fancy about this analysis because it's a woven composite. It doesn't matter. You just treat the woven layers like single lamina layers in a unidirectional stack, right? So very similar type of analysis. Okay, so that's problem number 1. All right, take a look at number 2. The battery's running a bit low, so I got to maybe move kind of quickly here. All right, 2 composites have been fabricated. One is a sandwich composite, one is not. Okay, first is an 8-layer glass epoxy cross-ply laminate. So 0, 90, 90, 90 is a metric. So it's 8 layers, etc. All right, the second is a sandwich structure whose face sheets are made from same glass epoxy laminate, but which now has a balsa wood core, such as the lamination sequence has balsa in the middle. All right, so 2 composites here. The first is like a 0, 90, 90. Okay, so it's 8 layers total. This is composite number 1. It's 0 on the top, 0 on the bottom, and then all these central layers are 90s. Right? Composite 2 is very similar, except it has a huge balsa core in it. Okay, so 0. And we have 3 90s here. Then this is all balsa wood. It's a very lightweight wood. And then now we have 90s. And then this top layer is a 0. So it's very similar. You have 0, 90, 90, 90, 90, 90, 90, 0. Very similar here. 0, 90, 90, 90, 90, 90, 90, 0. But then all this balsa wood here for this sandwich composite. So this is a sandwich here. Right? So it's asking you to calculate the A and D matrices for each of these composites. Then calculate the ratios of the individual entries of the A and D matrices. Right? So this is just laminate analysis, right? You're given the lamina stiffness matrix for a single layer of glass. You're given the lamina stiffness for the balsa wood. Now it's up to you to just build the A, B, and D matrices and compare them. All right. So remember, A matrix is summation K equals 1 to N of Q bar K ZK minus ZK minus 1. Right? Remember what each of these is? This ZK minus ZK minus 1, this is a Z height. So Z is the Z height. It's the height from the center of the stack. So remember, typically we have a coordinate system for these laminates that looks like here X, here is Z. Okay? So this would be the dimension Z0. This is the dimension Z1. This is the dimension Z2, etc. All the way up to the dimension here, which would be Z9, I believe. All right? Similar with like the balsa wood, you have a coordinate system that sort of ends in the middle here. And there's Z dimensions, all right? So this is Z0, Z1, so on and so on and so on, okay? These Z dimensions go like all the way down, etc. Okay? We're told typically each one of these layers is 0.25 millimeters thick, right? So each of these layers here is 0.25 millimeters. But interestingly, in the sandwich composite, we're told that the core has a thickness of 30 millimeters, right? 4 millimeters, sorry. But this here is 4 millimeters. Okay. So we have 4 face sheet layers, each 0.25 millimeters. That means this is 1 millimeter thick. And then here we also have 4 sheets that are all 0.25 millimeters. So this is also 1 millimeter thick. Right? So what happens is you end up with, like in the sandwich, Z0 is like negative 3 millimeters. Z1 is negative 2.75 millimeters, right? So I'm talking about like this dimension here, Z0. The distance from the middle of the stack down to the bottom of the laminate is negative 3 millimeters. You have to go 2 to get there and 1 more to get to the bottom, all right? That's different from the standard composite, where Z0 is only going down to the bottom of the stack. So here that's just this dimension, which is 1 millimeter only. You only have to go 1 millimeter. So the Z dimension is negative 1 millimeter. Z1 is negative 0.75 millimeters and so on. Okay. So it's really the only difference between the two composites is the Z values. The Q values aren't changing that much. It's this secondary term that really changes. And it's most pronounced with the calculation of the D matrix. Because the variables are cubed. Remember, this is ZK cubed minus ZK minus 1 cubed. And this cube really changes drastically the entries and the values of the D matrix. So not going to go through all the calculation. You can do the computation yourself. But the point is, you'll see the following for my batteries run out. Hopefully this doesn't cut off. But for the sandwich structure versus the standard composite. Okay. So for the sandwich, here we go. And for the standard composite, Here we go. So what you want to notice is significant differences in the D matrix. So here, this is times 10 to the negative sixth, and here's an entry of 0.26. Here's this 10 to the negative 7 and an amount of 0.18. So these are varying by about 20x difference, right? However, the A matrices are not particularly different. They're about the same. So they're approximately equal to each other. So it's just really interesting that the A matrix, which is the matrix that tells how much strain you get with tension, not a lot of difference, but the D matrix, which tells you how much curvature you get under bending, there's a tremendous difference. And that all is because of the core of the structure. All right. If you want to see the actual ratio of these guys, you could do that computationally as well. And you get something that looks like this. If you wanted the ratios calculated exactly, here are the typical ratios. And so, like I said, the ratio of the A matrix of the sandwich structure and the A matrix of the typical laminate is pretty close, or almost exactly the same, right? The value here being 1 means that the ratio is very, very close to 1 being almost the same. But the D matrix, the entries are quite a bit different, or approximately 20x difference. So it's telling you that the sandwich structure offers about 20 times more stiffness and bending than the traditional laminate. All right. So really interesting stuff there. All right. My battery's almost dead. I got to stop the video. Hopefully this was helpful. Good luck on the exam.